Hello grade 11 students and welcome to the second section of chapter 15, the electric field. In this section we're going to cover two main ideas, which are the electric field produced by a point charge and the electric field between the plates of a capacitor. Starting with the electric field produced by a point charge, supposedly Q, produces an influence on the region surrounding it. This influence is referred to as the electric field of this point charge. At a certain point, found at distance r from charge Q, the electric field is given by E equals K times Q over R squared along direction UR. What is UR? We're going to talk about it in a minute. First, note that K is called the electrostatic constant and its value is around 9 times 10 to the power 9 expressed in SI units. Now, representing the electric field of a certain charge, the charge itself is a point. Electric field lines are going to be drawn as radii, as if they are radiated from the charge itself. Imagine that we have circles around the charge and the electric field lines extend as radii of this circle. This is the meaning of radial direction. By a certain convention, UR is assumed to be positive when it points outwards or away from the charge or the center, and it's negative when it is inwards or towards the charge itself. So this is minus UR. This explains the presence of UR here along with charge Q. This will affect the direction or the sense of the electric field when we draw it or when we want to represent it. The relation is E equal KQ over R squared along UR direction. Thus, the vector related to electric field or representing the electric field has the following characteristics. The direction is always radial along the radius, or imagine lines going or radiating out or towards the charge itself. The sense differs according to the charge. We said Q times UR gives the direction. If Q is positive, then it's going to be along plus plus UR, which is pointing outwards, if you notice here. And if Q is negative, electric field lines point inward towards the charge. Another thing I'd like you to notice in the figure here is the size of the arrows. The closer we get towards the charge, the longer or the larger the electric field becomes. This is revealed by choosing larger vectors to represent electric fields. The magnitude of the electric field is given by KQ over R squared, and here we take Q as absolute value. No need to worry about the sign. Pay attention, units should always be SI units. So R must always be expressed in meters, not centimeters or millimeters. Q is in coulombs. Thus, the electric field would be expressed or given in Newton per coulomb or volt per meter. Keep in mind, 1 volt per meter is equal to 1 Newton per coulomb. So whichever unit you prefer to use, feel free to do. However, abide by it throughout the whole exercise. Let's put what we have discussed in an application. Two small spheres A and B lie on the x-axis as shown in the figure. Sphere A has a charge of plus 3 times 10 minus 6 coulomb, while sphere B is, which is 0.8 meters to the right of A, has a charge of minus 5 10 minus 6 coulomb. So pay attention, AB is given to be 0.8 meters. Okay, so if you want to find anything, you can start from here. Then we are given the values of each of the two charges. Part 1, list the characteristics of the electric field produced by each of the 2 point charges at I. Here is where we are interested in drawing the fields or representing them. If we discuss each of the 2 charges, QA and QB, first QA is positive. As we know, positive charges produce electric fields going away from the charge itself radially, as if I'm drawing here like radiations coming out of the charge. These are not radiations, these are just field lines, virtual lines. I'm interested with the field at I, so if I imagine AI to be joined by a radius or a direction, this is the direction of the electric field of A at point I. I can write it in this way. Some people might write electric field at I due to charge QA. This is correct. Electric field of A or QA on point I is also correct. It's up to you. No matter which form you use, however, keep in mind that you're going to be using it throughout the whole exercise. Now, if you consider the second charge, which is B, QB is negative, so field lines, as we have seen, point towards B itself. Again, these are not radiations. They are just representations to imagine where the electric field due to B is present. At I, that electric field is going to be in this direction, electric field of B on I. So this is in brief how I'm going to discuss this exercise. Notice that I'm interested only in the electric field at I and not anywhere over here. As for the solution, okay, here you can see the direct calculations. Let's discuss them. First, if we go to the electric field of QA at I, notice the notation. This electric field has four characteristics. The point where it is drawn, the origin, it's applied at I, so we just draw it at I. Same thing for EB. Now, as for the direction, it's along the line joining A to I, which is, as our figure shows, which is along this. I'm going to draw here a rough sketch, A and B, QA and QB. This is point I. So at I, I'm going to draw the vector along AB, along this line. And since QA is positive, I'm going to draw the vector in this direction. So this is EA at I. As for the magnitude, K, Q over AI square, note that AI is 0.4 meters because it's half the distance AB as given. Replacing values, note that AI is in meters, so it's safe to keep it 0.4. 310 minus 6, simple calculation, we get this value. Electric fields are usually of large values, so don't feel wrong or bad about getting a large value. The value is around 169,000 volt per meter or Newton per Coulomb. We can use either of the two, but if you notice in the second part, I have chosen Newton per Coulomb just to continue with that. Okay? Once I finish these, I'm going to talk a bit about this unit, Newton per Coulomb. Now, I represented the vector here, just a rough sketch, regardless of the values I've used. As for the electric field of B at I, as we said before, QB is negative, so the electric field is at I towards B. Here it is. Now I'm left with one thing to do, which is the value of EB. Replacing values, notice that absolute value of QB is 510 minus 6. We just drop the negative sign. We get 281,000 Newton per Coulomb. As EB is larger than EA, it's obvious that we have to draw electric field of B at I with larger measure than EA. Now, before I move on, Newton per Coulomb, if you analyze the unit itself, let's say here I have 169,000 Newton per Coulomb, it means that the electric field results in a force of 169,000 newtons, which will be acting on each Coulomb. Okay? This reminds me of when we say 10 Newton per kilogram as for the gravitational field, right? Meaning, gravity pulls each 1 kilogram by 10 newtons. So using Newton per Coulomb here as a start gives us a good or a nice idea about what electric fields stand for. Now, if we want to represent it, actually, we have the x-axis drawn along line AB, so we just take the two vectors, EA on I and EB on I. Since we said that EA on I is towards the right side, or towards at A towards B, or at I towards B, two values are given. All I have to do is just choose a convenient scale and draw these two vectors, 281,168. Once we've drawn these, we notice that the two electric fields point in the same direction, and this will lead me to answering part 2. In part 2, you were supposed to calculate the net electric field. Since the two vectors point in the same direction, so we can simply add their values, and the final direction is going to be the same one, which is plus I. And this is everything related to application 1. The second section for this video is the electric field between the plates of a capacitor. What is a capacitor before we start? It's simply an electric device used to store electric charge or electric energy. We're going to see it in a moment. By the way, we're going to have a full lesson dedicated for capacitors. We're going to talk about these in more details. The plates of a capacitor, which is made up of two plates, the capacitor usually, one plate and the other one, they are usually separated by something, by an insulator between them so that they don't touch each other. The two plates will carry charges, positive on one and negative on the other. This is how a capacitor looks like, a parallel plate capacitor. Two plates separated from each other by a distance d. One of the plates is charged positively with a charge QA, while the other is charged negatively with an equal value minus QA. The plates of the capacitor will be connected to a voltage source, maintaining a voltage UAB between the plates. Thus, we're going to obtain a uniform electric field. The word uniform might be directional, indicating that uniform direction, or it can be as in magnitude. Usually, we use uniform as direction, not magnitude. However, for this level of your course, what you need to know as grade 11 students, electric field between the plates of a capacitor is constant and uniform. If you just use the word uniform, it's okay, it's accepted. However, it's not general. Okay? Keep this in mind. The direction is always from the positive plate to the negative plate and perpendicular to the plates themselves. This is how we represent it. Looking as a side view or frontal view of the capacitor, you see the positive plate here, plus Q, and the negative plate here, minus Q. Electric field lines are pointed from positive towards negative, perpendicular to the plates, and all lines are parallel to each other. Unlike with a point charge where electric field lines intersect, in the case of parallel plate capacitor, the field lines are parallel to each other. Moreover, the magnitude is given by E equal U over D, voltage over distance. You just take the voltage between the plates and the distance between the plates, and you're going to get the electric field. The magnitude is expressed in volt per meter here. That's why we said volt per meter or Newton per coulomb. They are alike. Volt per meter is used from this equation. Newton per coulomb is a general indicator of the electric field unit. Application 2 targets the electric field between the plates of a capacitor. A parallel plate capacitor is charged under a voltage of 5 kilovolt and the plates are separated by 1 centimeter. Question 1. We need to draw a figure showing the plates of the capacitor and the charge on each plate. Then we need to list the characteristics of the electric field within this capacitor. Let's move to the solution now. First part, we are required to draw the figure. Feel free here to draw a figure in 3D as it's done here, or simply just draw two lines representing the capacitor itself. This is the capacitor, okay, with the positive charge on one side and the negative charge on the other. Now, there is no convention for where to place positive or negative or how to draw the capacitor, except for two lines being parallel to each other and having this connection from each of the two plates. The second part is to list the characteristics of the electric field between the plates. We know that the electric field is uniform, okay? That means it has one direction from positive to negative as we know it, and we also know that's going to be constant. So the characteristics are the following. Direction is perpendicular to the plates, sense from positive to negative, and magnitude, which is given by this equation, E equal U over D. Remember, U should be expressed in volt, D should be expressed in meters. Now, if we go back to the given, we notice that U is given to be in kilovolt. U is given to be 5 kilovolt. So we directly convert that to volt, which is 5,000. We know that a kilo is 1,000. Distance is given to be 1 centimeter. Divide by 100, we get 0.01 meter, which is the SI unit. Replacing now the values, we get 500,000 volt per meter. Remember, volt per meter or Newton per coulomb are the same, or they are equal units. The question proceeds to ask us to represent the field vector. So according to what we have discussed here, we just add the two plates, or simply we can use this figure as well. Okay, however, here just for the sake of clarity. Then we draw the two fields, or the field lines, sorry, between the plates from positive to negative, perpendicular to the plates. Now, as for the value, we don't need to indicate that. Now, a note before we move on concerning the electric field between the plates of a capacitor. It is uniform and it depends on the voltage and the distance between the plates. It's important to notice and to use the voltage and the distance corresponding to that voltage. The problem states that the voltage between the plates is 5000 volt and the plates are separated by 1 centimeter. So we just used corresponding values for voltage and for the distance. That's all for this application, and that's all for this section. Summing everything up, we notice that we've covered the electric field of a point charge and the electric field between the plates of a capacitor. This is everything we need to know in this section and what you need to memorize. So focus on this page. This is what you need to carry on when you move on to the problems section or to the applications. For that, I've chosen these two exercises. You can pause the screen and solve them, or if you are using the CRDP book of grade 11, go to pages 238 and 239. You can find these as exercises 5 and 9. Solve them and we can discuss them later. That's all for this section. Thank you for your time, and we still have one more section to end up this lesson. Have a nice day.